So we're up to our fifth and final lesson for Unit 2 for AP Calculus. And it's another day that we're going to be looking at these things called derivatives. And what we saw last day with our first day of derivatives is that we now have a plan for finding the exact slope of a tangent line, one of the two main questions in calculus, just by taking a secant line and then sliding that second point closer and closer to the point where you want the tangency to be. The drawback, though, was that we had to pick the point right away before we started doing our limits. We called it A in the notes, but it was actually some number. So if I was to just go back and take a look at our notes here, this was from the other day. We said, oh yeah, you're located at A, and then the second point, which will slide towards it, is a little bit different for its x value. It'll be A plus H. And H could be plus or minus, right? Could be a negative number 2, so maybe the second point's a little behind it. But you had to pick the A right away. Case in point, let me just find one of the examples we did. This example here, where if you take a look at the question, it says, oh, well, let's begin at x equals 3. And we knew we were going to start at 3. And then all of the algebra that we did, you can see the 3's all over the place in there. And the answer that we got, it was impressive we could do it, but it was specific to being the slope located at x is equal to 3. So what I'm wondering now is there a way we can make this more generic? Instead of saying, oh yeah, you're located at A, could we keep this wide open? Could we actually just call it like, I don't know, x, like we've done every other time in algebra? And then we'll come up with a new chunk of algebra, a new machine, a new function that will actually be the slope anywhere you want on the graph of y equals f of x. And that's where we're going today. So we're a little farther down the road. We are going to be this page right here. All right, so now we're going to take a look at derivatives as being new functions. And we've got this little apostrophe notation again, which we pronounce as prime. So this is pronounced f prime of x. It's a new function that will tell you the slope. It generates the slope of f of x at all x values that you could want. This new thing called the derivative, it's different from f of x. It's not the same thing, but it's definitely related to it because it'll be the slope anywhere. So what you can see is it's the exact same deal we had before. It's nothing but y2 minus y1 all on top of x2 minus x1. That's all that's happening there, just like last day. The only difference is we're not going to say, oh yeah, you have to pick a constant, like A or 3. Instead, this number here, it's just going to be a general x, okay? So this is not a constant. But we can still go through the plan of doing the limit and then see what happens. So let's try it out with this function here, x cubed. It's going to be a bit of a grind to go through x cubed, but we'll see how this whole deal works. So I'm going to make a whole new function called the derivative, pronounced f prime of x when you see it like that. And it's going to be a limit because we're going to take that nice grade 10 slope calculation and then bring those two x values really close together. So it's a limit as h goes to 0, and it's going to be our function figured out at the second x value. So that's x plus h. I don't know what the x is, so I'll just call it x for now, right? So this is wide open what that's going to be. And then subtract off f at x. Again, we don't know what this number is. So we're at that number, and then we're a little bit past that number, x plus h. We'll divide all of that by the difference in the x's. You really should write x plus h minus x, but that's always just going to be an h. Okay, so in this story, taking a look at the function that we're playing with, in this particular example, they're saying, hey, can you try this out with x cubed for your function? Yeah, sure. And then it'll look like this. We're going to have to insert into the cubing function that second x value, x plus h, and then put in the first x value, which is just going to be x. So I'm not going to lock in. I'm not going to say, oh yeah, let's do it at 5. I don't know. I'm not too sure where I'm going to be doing it at, right? So this is a big unknown right now. Like, where will you actually want to go and find the slope? I don't know. I'll tell you later. Okay, well, that first binomial being cubed, yeah, that's a lot of work. Okay, so let's see what we get here. So this derivative, I'm going to write this a few times, getting used to writing it like that. Limit as h goes to 0. Okay, so we have to go and cube that x plus h. that means x plus h multiplied by another x plus h multiplied by another x plus h. Wow, that's a lot of cubing here. Minus x cubed. It's going to be a lot of multiplying. And now it's time to start FOILing that all out. There's no quick way to do that. It does not turn into x cubed plus h cubed. It's way more interesting than that. Let's see if I can sneak another line in here. I'm going to put two of them together, but maybe just leave the first one. So here, the first one's all by itself. Now let's blend these two together. So we'll have x squared plus a 2xh plus an h squared. Okay, still minus the x cubed on the end. Can't forget that. Students often do, but we're not going to forget it. Okay, more multiplying in order to get this to work. So this derivative, this function that's not f of x but sure is related to it, well, what's it going to actually look like? Well, we're doing a limit as that h goes to 0. Last little bit of distributing here. All right, we're going to have an x cubed, and then there are two terms that have x squared h. There's a 2x squared h and then another x squared h. So those like terms go together to become 3x squared h. So yeah, it might take you a little bit of multiplying that all out to see that. Then there are two terms that are x h squared. There's a 2xh squared and then there's a 1xh squared for a grand total of 3xh squared. Take your time to actually do that FOILing if you need to, right? You're going to have to distribute in there like lots of different multiplications. Okay, then there's also going to be an h cubed. Now that's just this first big mess of the binomial multiplied by the trinomial. I still have this subtract x cubed, right? That's the first y value. So I've got to say, yeah, subtract that. And all of that is sitting on top of h. Now, something nice always happens with these limits here. We've got the terms that don't have h in them. Oh, they're going to self-cancel, right? X cubed minus x cubed, they go away. That's actually critically important, because if that didn't happen, we wouldn't be able to do this nice GCF factoring with the h in order to deal with this limit that we're trying to solve. So h is still going to 0. And now with the terms that are left, I am able to factor an h out, and I would have 3x squared plus 3xh plus h squared, all sitting on top of an h. Okay, well, I can reduce. I can say, well, as long as you promise not to put 0 in, but you're only going to be close, we could actually go and reduce those h's. All right, next line. Now, you might not write this step out every time, but I'm going to put it in here. I'm now left with this limit as h goes to 0. That's actually pretty nice to do. I have a 3x squared plus a 3xh plus an h squared. And h is going to head towards 0. This function is now continuous in h, so I can happily go and do direct substitution and put 0 in for h. It's going to go in here, and that wipes those terms out. And what I end up with is this answer 3x squared. So that is the slope of f of x at any spot that you want to check. Okay, so kind of thinking about where we're at here, I'm just going to summarize that again over here. The original function was x cubed. That'll tell you y values on the graph. And what we've just found is at any moment, if you want to know the slope, you could just evaluate this, and it'll tell you the slope at any x value that you want. So down here in example 9, it says find the instantaneous rate of change. In other words, this big phrase here, that's just like saying, yeah, could you please find the slope of the tangent line, right? That instantaneous slope for x cubed. Well, that's what we've just been working on. Can you do it at x is equal to 3? Sure, absolutely. It's actually really easy to do. What you're asking me to do is f prime of 3. You want me to evaluate the slope at 3. No problem. That will be 3 times 3 squared. 27. The slope will be 27 there. And if somebody said, oh, I'm sorry, did I say 3? I really wanted you to find the slope at 4. not a problem. If I had gone through my limits with the number 3 in there all the way through, I'd have to start all over again. But here, all I have to do is say, oh, you want to put 4? Oh, yeah, sure. We'll find the slope exactly at 4. So that'll be 3 times 4 squared. That ends up being 48. So it's incredibly flexible. I'm able to find the exact slope of a tangent line, but I haven't even decided where I'm going to be doing this exact slope. It's like, yeah, I'll decide later where I want to do it. And that's this whole idea of thinking of this derivative as being a whole new function, this f prime of x. And it works really, really well. Okay, for the next 3 pages, we're going to compare and contrast these two methods. We're going to do both methods for each one of these questions. That's why the little note there says make sure you're ready to do either one of these if you're asked to on a unit test. So find the instantaneous rate of change. In other words, find the slope of the tangent line, right? That's what this is saying, right? The right now rate of change means slope. So the right now slope of that parabola at the point where x is equal to minus 2. So they want us to actually go and put in -2 at the beginning for this first approach. So this is actually like last day. They're saying, well, could you go and do f prime, and it's going to be at -2. We're sure of it, absolutely sure. We won't change our mind. Okay, so that's going to be a limit as h goes to 0. I'm really doing nothing but a nice little grade 10 slope calculation. I've got my second y value, f at -2 plus h, minus my first y value, f at -2, all sitting on top of h. That's my plan. It's just that doing f of -2 plus h is a lot of work, right? So we better get at it. Here goes. Doing the limit as h goes to 0. All right, so this numerator is going to turn into a big, ugly mess. I'm going to just use some red brackets to organize things here. This is going to be f at -2 plus h. So I would have to go, looking at the function, 3x squared. Whatever goes in, triple it, triple the square. Okay, so 3 times -2 plus h squared. Then moving on, minus 5 times what you put in. Minus 5 times -2 plus h. Add 7. Okay, all of that, I'm nowhere near done. All of that is me just figuring out f at -2 plus h. I have taken this binomial and gone and inserted it into the function just to see what I get. Great. But now I have to go and subtract f at -2. Okay, again, maybe just to help organize things, I'll use some red brackets here. So in goes -2. That'll be triple -2 squared minus 5 times -2, add 7. Because that's what the function tells me to do, right? I'm looking up here at the function to see what to do for that. So every question's different in terms of what that numerator will look like. But every question's the same for the denominator, h, just that difference in x values. Okay, time to expand this out, see what we're working with here. I don't have a lot of room left, so we might have to kind of do a couple of these steps here at once. We're going to have this binomial getting squared. Maybe I'll leave the 3 out there for a moment just to be safe. I'm going to have a 4, then multiplying and doubling minus 4h, squaring h squared. There's going to be a 10. There's going to be a minus 5h. There'll be a 7. And there's going to be a minus 12. And then there'll be, lots of negatives here. -10. Oh, plus 10. Oh, -10. Triple negative. And then finally minus 7. All sitting on top of h. Now what you're going to notice is the terms that do not have h's, they're going to need to go away if we're going to have any success with this limit. And sure enough, they do. Like for instance, this 3 times the 4, that's 12, but then here's minus 12. So let's get rid of the minus 12 and the 12. I'm just going to scratch the 4 off. What else have we got? 7 and -7. And, a 10 and a -10. And all of the terms that do not contain h are now gone. And we're left with just terms with h's. So we'll be able to do a GCF factoring. So I'm going to have a limit as h goes to 0. Let's see what we're left with. there's going to be a minus 12h plus a 3h squared and minus a 5h. And all of that is sitting on top of an h. Okay, well, let's repackage this here a little bit. We're going to have a limit as h heads to 0. Okay, I'm going to factor an h out. So extracting the h, there's going to be, there's this 3h squared, so that'll be just like a 3h, and then there's this negative 12, negative 5, those are like terms, so we'll have a negative 17, I can write these in either order, plus a 3h. All sitting on top of an h. Now remember, you're not going to put exactly 0 in, only numbers close to 0. So it's totally okay to say, well, that factor and that factor are identical and they're not 0. Let's cancel them off. And then this binomial that you're left with, negative 17 plus 3h, that one's continuous. You're good for doing direct substitution. Now let's go and put 0 in for this h. So 3, when you do that, when you put in 0 in here, 3 times 0 is 0. You'll have negative 17. So with a little bit of work, we were able to find that the exact slope of the tangent line is negative 17. That's actually really cool that we can take this graph, it's a parabola, and we can say, you know what, with certainty, the slope of the tangent line is exactly negative 17, as long as you're standing at negative 2. But we've done so much work here that is specific to the point x is equal to negative 2. And if somebody said, oh, did I say negative 2? I meant to say negative 20. Then you'd have to start all over again. So let's contrast that with b, just this task of finding the derivative in general, the whole new function that works all the time, including at negative 2 for this function here. Okay, here goes. It's going to look very similar. This f prime of x, it's going to be a limit as h goes to 0. We're doing a little grade 10 slope calculation. So we've got to set up our y2 minus our y1, all on top of our x2 minus our x1. I need a big long line here. Okay, I'm going to put in x plus h into that function. And I might need some little organizing brackets here. Okay, here goes x plus h. We're going to have triple x plus h. So it's very similar to the top of your page, except we had a negative 2 there. Here I'm saying, well, I don't want to lock myself into negative 2. And then minus 5 times x plus h plus 7. So it's the exact same as the top of the page, but without committing to negative 2. Subtract. Now, let's just put in x, this non-committal location of x. We'll have 3 x squared minus 5x plus 7. All sitting on top of h. Okay, well, let's go ahead and FOIL that all out, and we'll see what we're staring at. Okay, foiling here, we're going to have an x squared and then tripled, so 3x squared. You're going to have xh and xh, two xh's when we multiply and double, then tripled, so plus 6xh. And then an h squared tripled, so 3h squared. Moving down the road, minus 5x minus 5h. Add 7. Minus 3x squared. Oh, double negative, plus 5x. And minus 7. So I have to watch how that negative affects everything in the trinomial, all sitting on top of h. Now remember, you're going to notice all the non-h terms, if we can call them that, are going to vanish, like 3x squared and minus 3x squared, minus 5x and plus 5x, plus 7 and minus 7. So that goes away quite nicely. And then we're left with terms that have h's everywhere. So we're actually going to be successful, we might as well do it right now, in doing a little GCF factor, a little greatest common factor factoring. So we'll have an h sitting out front, then what's left? Well, it looks like we've got this 6x sitting there after the h comes out. We'll have a 3h, yeah, okay, great, got it. minus this 5, and everything else is gone. Just sitting there like that. Now we're not going to put 0 in, we're only putting numbers close to 0 in, so we're okay in saying, well, this really small close to 0 number and that really small close to 0 number, they're going to reduce. And now we have this little trinomial there. It's beautifully continuous in H. It doesn't have any holes in it. So now you can put 0 in. You can do direct substitution. So 0 is going to go in for H right here. And 3 times 0, of course, is 0. It goes away. And so we're left with this answer. We're left with this machine. We call it f prime of x. It's called the derivative. And this machine, it is not f of x. You know, f of x was that big trinomial, 3x squared minus 5x plus 7. This is a new machine. It's related to f, so it's got the name f in there, but it's f prime. And this machine here, 6x minus 5, will tell you the slope anywhere. So if later on somebody says, oh, well, I needed to do it at -2, like we did at the top of the page, fantastic. Put -2 in here for x, and you'll get -17, like we did at the top of the page. Put -100 in, and you can go, oh, okay, well, it's like -605. You can do any number you want now to instantaneously find the slope. So that's what it looks like to do those two methods on just some nice, polynomials. That was a nice little trinomial there, a little parabola. Let's try it out with a radical to see what that looks like, something with a root in it. Same plan, top of the page, we're going to lock in on a number, x equals 11. Now, the bottom of the page is going to be better. It'll be way more flexible, and we'll have something that you could have just put 11 in anyways. All right, let's get this rolling here. We're going to do f prime at 11, specifically at 11. So we have to do a limit as h goes to 0. Doing a grade 10 slope calculation, and what I'm about to write down right now is just, it's a big, long, ugly fraction, but I'm going to do y2 minus y1. And I'm going to put all of that on top of x2 minus x1, which always turns out to be an h. Okay, here we go, the top, the difference in the y's. Our two x values are x and x plus h. Let's put the second one in first. So putting in x plus h, I'm going to have the square root of, well, it'll be a bit messy here, 4 times x plus h, right? Because the function says whatever goes in shows up here like that. All right, then add 5. There, that's the original function. Now on the last page I had some brackets there just for organizing. I don't need them here because the root sign behaves like a bracket. But if it makes it easier for you to see, sure, for one line I'll put some brackets in here like that. Okay, now let's go and put in the first x value, which was just an x. Oops, done this wrong here. I should have been putting 11 in. My mistake. Actually, well, it's a good little learning moment. Right here, we're specifically putting in 11. So our points are 11. I apologize for that. 11 and 11 plus h. So now I'm just going to put the 11 in. Sorry for that. Okay, so we'll have here 4 times 11, then add 5. All right. Ooh. That is not a fun limit to do. You can't do direct substitution because you'd have division by 0. So we're going to have to try cleaning this up a little bit. Let's look and see what the next line reveals for us here. We can do a little bit of simplifying inside those radicals. So, still have my fraction on the go. 4 times 11 is 44, add 5 more is 49, and then we'll have a 4h. So we're going to have this, 49 plus 4h. You cannot root those two numbers separately. That is not the same as the root of 49 plus the root of 4h. Doesn't work. Can't be done. It's got to sit there like that. Here, 44 and 5 is 49. Okay, that one is just the root of 49. That one is just going to be a 7. That's fine. But there's no simplifying you can do to break this radical open. And all of that is sitting on top of an h. Again, I still can't do direct substitution of h equals 0, so I need a plan. And this is my plan. I'm going to use the conjugate. I'm going to take this whole big top and the bottom two, I've got to be fair, and I'm going to multiply them both by something that will make the top a nice rational number. And what I know works is this conjugate, this 49 plus 4h, leave that, but then switch this minus to a plus. That will be really nice. But if you're going to do that in the numerator, to be fair, you've got to do it in the denominator too. Or at least you have to tell people that you're ready to. And I say that because I'm not actually going to multiply the bottom out. If I did, I'd only have to factor it back later. So I'm going to leave the bottom as just two things multiplied together. But the top, oh, it's beautiful when you do that. Okay, let's take a look here. Our f prime at 11, it's a limit as h goes to 0. Okay, when we go and do the foiling, if you want to call it that, we're going to have this root multiplied by this root. That makes a nice honest root, like a nice honest whole number, right? If you multiply those two roots together, we're just going to have 49 plus 4h. Then the outsides and the insides are opposites. You're going to have a 7 times the root minus a 7 times the root. That's why we do that. That's why we use the conjugate. So that goes away, and then minus the 49. Oh, that's looking pretty nice. Down in the bottom, just say you're going to multiply it out. Just go, yeah, there's an h. Okay, this one right here. And then multiplied by this conjugate. Yeah, I was making sure I was being fair. So I have this here, 49 plus 4h, and then add 7. But don't actually multiply it out. And the reason why is this. If you take a look at what happens after the 49s go away, we're going to have the limit as h goes to 0. And I like the fact that there's an h just kind of isolated down here on the bottom, because up on the top I have this 4h. So yeah, this h right there is beautiful. Then the root, 49 plus 4h, add 7. Okay, so the h's, we're not going to put exactly 0 in, just things that are close. So that goes away, and now you can do direct substitution. You don't get division by 0. If you try putting, oops, too many apostrophes. If you try putting in h equals 0, you're going to find that this is the root of just a 49. Well, that's a 7, and then this thing turns into 4 on top of 14. Or if you want, you can reduce that down to 2/7. So this is a very specific answer. It's the slope of a tangent line right at that moment when x happens to be equal to 11. It's the only time that it actually works. It doesn't work at x is equal to 12, but it works at 11. And we did that by putting in an 11 very early in the problem. Now I accidentally put an h in there. That's actually the bottom of the page. If somebody said, oh, I'm so sorry, did I say at 11? I meant 511. Then you'd have to start all over again. So this time, let's play the same game, but where we put in an 11, let's just keep this wide open. Let's put in just an h and then watch what happens. So we're just going to find the general derivative now. So f prime of x. Let's get this to where we can see it a little bit better. It's just a slope and then a limit, right? So it's a limit of a slope. H is heading towards 0. Okay, I've got two different x values. The x values are x, right? That's one of them. And the other one is x plus h. And I need to put those into the function to see what I get. Looking at putting in the second one first, because that's how we did it in grade 10. We went y2 minus y1. I'm going to have 4 times x plus h, then add 5. Take away. Now let's put in the first x value. Square root of 4x plus 5, all sitting on top of just an h. Okay, well I can expand that open a little bit. I can tidy it up slightly. Probably could have skipped right to this line next time. Just a tiny little bit of work I can do in there. I can distribute the 4. It's still all going to be underneath this root sign though. I'm going to have 4x plus 4h plus 5 minus this root, 4x plus 5, all sitting on top of h. Direct substitution does not work. You can't put h equals 0 in because of this division by 0 that would happen in the bottom. You also cannot split this up into separate roots. That is not the same as the root of 4x plus the root of 4h plus the root of... That does not happen. But we could use the conjugate. We could go and very carefully give this whole top a bump with its conjugate, which would be almost the same thing, but it's going to have a reverse sign right in the center. So if that has a minus, let's put a plus in. All the signs that are inside the roots, I'm going to leave them. Now the bottom, I'm going to tell people that I'm going to do this too. Well, at least I'd be willing to do it. But don't actually do it, because we're going to probably find, well, we will find that h in the bottom is going to be reduced. So we want to see it hanging out there all on its own. Okay, well, what happens when we go ahead and do that? Right, and get that beautiful foiling, kind of creates what we would call a difference of squares in math. The middle terms go away, the outsides and the insides. All right, we're going to have, I'm going to use some brackets just sort of for emphasis here. When these two roots multiply together, they're identical, so we're just going to have the trinomial. We're going to have, I'll go with my pattern of using red. We're going to have 4x plus 4h plus 5. There, that's my firsts. Then the outsides and insides cancel, right? That cancels with that, so we don't even have to worry about it. And then the lasts, when those last two roots multiply together, we're going to have subtract, and here comes what you have with the lasts. Just simply 4x plus 5. All sitting on top of an h. Okay, here comes the magic. Well, it's not magic. Here comes the nice math. All the non-x terms are going to go away, like 4x minus 4x, 5 minus 5, and you're only left with things that have h in it, right? Which is exactly what we've got here. Oh, except I have forgotten to write in this other part with the conjugate. Super important. That was still waiting here. Remember, we talked about just letting it sit there. Don't actually distribute the h through. That's because of what's going to happen right here. The top has simply become 4h. That's all that's left, right? It's right here, just that 4h. And it's sitting on top of this h times all that mess. So we can go and reduce these h's. As long as you promise to put numbers in that are only close to h, there, that h is gone and that h is gone. So we're left with this limit to go evaluate. It's actually going to be quite nice. It's a limit as h, that spacing of the x values, heads towards 0. And what are we left with? In the top, just a 4. Okay, this 4 right there. And then in the bottom, we've got this root of 4x plus 4h plus 5. Okay, well, if you go and do a limit as h goes to 0, then that's just going to be 4x plus 5. And then this other one looks identical to that. 4x plus 5. So I'm doing my substitution of h being 0 now after I've reduced those h's top and bottom. And I have that, which if you want to, I mean, it's correct, it's done. But if you want to, you could rewrite that and say, oh, look, I've got two identical roots down there in the bottom, two 4x plus 5s. And if you're going to go that far, you might as well reduce the 4 and the 2 and say, here's my final answer. 2 sitting on top of the root of 4x plus 5. That will tell you the slope of the original function anywhere, including at 11, which we did at the top of the page. If you put 11 in here, 4 times 11 is 44, add 5 is 49, take a root of 7. Yeah, 2 7s. But this works anywhere. So somebody could say, well, let's do it at, I don't know, x is equal to 1, right? You could do, oh, okay, you want to know the slope at x is equal to 1? 4 times 1 is 4, add 5 is 9, 2 over the root of 9, 2/3. So it works in any spot that you want to check, which is super nice. So that one had a radical. Let's do kind of the last of the kind of big ideas here. Let's do a rational. What about a fraction of algebra? Okay, this is going to get a little messy, but we've got a technique to deal with the mess. And we're going to begin by doing this one right at x is equal to 2. Okay, that'll be our first place to work. And I'm not going to make the same mistake I did on the other page. I'm going to put 2 in at the beginning. So they're saying, please see if you can go and find the exact slope at 2. So our 2 points for x are 2 and a little further away from 2, 2 plus h. You can imagine that being a little farther to the right, although it could be to the left as well if h was negative. Okay, so this is going to be a limit as h heads towards 0. Now, the mess. We have to go and put in 2 and 2 plus h. Let's put the second x value in first. I have to put that in right there. Oh, this is going to be a 3 sitting on top of 4 times 2 plus h, then take away 5. Subtract what happens when you simply put a 2 in. 3 sitting on top of 4 times 2, take away 5. Ooh, all sitting on top of h, the difference in the x's. Ooh, that's a bit messy. Let's see if we can tidy this up here a little bit. I'll work to the right. Okay. This first fraction, got a fraction inside the fraction. It's a mess. 4 times 2 is going to be 8. Take away 5 is a 3. This is like 3 plus 4h. And then we're going to have this. I can write that as, what do we have here? 3, and then 8 minus 5 is 3. Oh, that's 3 on top of 3. That's just a 1. Okay, great. And all of that sitting on top of an h. Okay, so you've got a fraction inside a fraction. That is a mess. Here's my advice. Let's take this entire numerator, and we'll take the denominator too. We got to be fair. And let's just go and multiply top and bottom. That won't change the value of a fraction by a number that will make it look nicer. I'm going to multiply by the least common little denominator. And I only see one little denominator, so I'm going to multiply this by 3 plus 4h. So that's going to distribute into here and onto the 1, but I have to multiply the bottom by it too. Okay, so what happens when we do that? We're going to have this f, that's a bit of a mess there, let's try that again. This f prime at 2, it's going to be this limit. H is heading towards nothing. Okay, what do we have? When this green binomial comes in and hits this fraction, it will reduce the denominator and we'll only have just a beautiful looking 3. Then it goes and hits the 1, so we're going to have minus. It's going to hit all that. That minus will hit it all. So minus 3 plus 4h. There, that's what happens when this green binomial comes in and hits that. In the bottom, why don't we just tell people that we would multiply it? Let's leave it like that. Okay, well, all of the non-h terms are going to go away. So in the top we just have a minus 4h sitting on top of this denominator, an h. Oh, I'm liking that now. Okay, as long as you promise to put in numbers that are only close to 0, those could be reduced. And now you can put 0 in because this expression, negative 4 on top of 3 plus 4h, it doesn't have any issues near h equals 0. It's continuous in that place. So now you can go and put 0 in here, and we're just going to end up with minus 4/3. Well, that's a very specific answer. That's what happens when x is 2. Let's try to do this generally with x being just left wide open. Okay, that's what part B says. Can you just find the derivative in general? So for part B, our two x values are going to be x and x with a little shift to it. And we'll see what we get. Okay, let's try this out. Basically the same plan. It's the limit of a grade 10 slope calculation. Okay, so we're going to have a fraction inside the fraction, right? There's this h in the bottom. But what do we have up in the top? Well, we're going to have the x plus h going in, so 3 all on top of. Now I'm going to put x plus h in where the x goes. That would be a 4x and a 4h. Okay, so 4x plus 4h, take away 5. Then just put x in. Then it will just look like the function description. Okay, fraction of fractions. Direct substitution is a failure. You can't put 0 in for h, not right now. Maybe later, but not right now. So you have to look around at the little denominators and find out what the least common denominator would be. So here's one of the denominators right here, and here's a different one. They're not the same number. Algebraically, those look different. So when I go to decide, well, what should I go and give this a little kick with, I have to go with the least common denominator, which in this case would actually be both of those factors. It's going to be 4x plus 4h minus 5. Also, though, just a 4x minus 5. In terms of algebra, those are different factors, because right now h isn't 0 yet. And I have to be fair and do the same thing in the bottom too. Or at least I have to tell people that I'm ready to do that in the bottom. The idea of multiplying by that big green mess is that it should make things look nice. It should clean things up so we don't have to look at a fraction of fractions anymore. All right, well, let's see if this is true. So this pair of factors comes in and hits this first fraction. Well, we'll have some reduction with the trinomial, but not with the binomial. The binomial will persist, and it'll touch that 3. So you're going to have 3 times 4x minus 5. And if you're wondering, well, where's that 4x minus 5 coming from? It's this thing right there. Okay? The trinomials cancel, but that binomial will persist and hang around. Now, the second fraction, when the green double factor comes and hits this fraction, the 4x minus 5 reduces, but the trinomial will persist. So you'll have 3 times 4x plus 4h minus 5, all sitting on top of just the h. Well, it looks a little better. At least it's not a fraction of fractions. Now, all of the non-h terms should go away. Let's see if it's true. We've got, looking at this thing here, a 12x minus a 12x. Okay, so I don't have to look at that and that. That's gone. I've got a minus 15 plus 15. Okay, those are gone. All right, so this whole double term here is gone, right? The 12x and the 15, right? And so the 3 as well, right? That's all taken care of. The only thing I'm left with is this negative 3 hitting this 4h, which is a negative 12h. I don't have to worry about this 3, right? It was going to get multiplied by those things that have now vanished, so that 3 is gone too. But this 3 will hit this 4h, so I'm going to have this limit. Oh, I missed something here, though. I still have these. I've done that twice now. Got to put that in there. Okay, refining this a little bit. See where we're at. This is a limit. H is going to head towards 0. And in the numerator, I've got a negative 12h. In the bottom, I have an h, and then these 2 polynomials. Well, if you're going to promise to put numbers that are close to 0 in for h, okay, then you can reduce those. Now, this expression that's left, it's actually continuous if you're near h equals 0. So now you can go and do direct substitution with 0 for h. This thing doesn't have any issues there. And so we end up with negative 12 on the top, and then this binomial, 4x minus 5, and then another binomial, 4x minus 5, both multiplied together. So my final answer for this is going to be negative 12 sitting on top of, let's make that look a little cleaner here, negative 12 sitting on top of a 4x minus 5 squared. Now when I said it doesn't have any issues when h is near 0, yeah, as long as the x value is such that we're not going to create 0 with this 4x minus 5. So this thing does have issues at 5/4. So does the original graph though, so that's not a problem. Part C, at what x values? So where would you be located on the graph? Will the graph of y equals f of x have a normal line with a slope of 3/4? Whoa. So a normal line is a perpendicular line. So you've got your graph cruising along, and then they want to have a line that's perpendicular to it, like this, right? Meaning at 90 degrees, and it has to have a slope of 3/4. Well, that's a neat story, but calculus doesn't work very well with normal lines. It excels at telling you about tangent lines. So what I would do right away is say, all right, let's take this story and let's just translate it here, right? If the normal line, if the perpendicular line has a slope of 3/4, then let's spin that around and let's talk about the tangent line. What's going to happen if you were to draw a tangent line in like that? That's tangent to the curve. Well, they're going to be perpendicular. And I know perpendicular lines have slopes that are negative reciprocals, opposite reciprocals of each other. So the tangent would have a slope of -4/3. Now we're going to play the game backwards. Instead of me saying, oh yeah, what about at x equals 22? And you go and say, all right, let me go find the tangent slope. Now I'm saying, well, is there an x value where the tangent does have a slope of -4/3? So we're going to take our creation that we had right here, and we're going to say, hey, are you ever equal to -4/3? -12 sitting on top of this. That'll tell you the slope anywhere, and I'm wondering, is there anywhere where that happens to evaluate out to be a -4/3? Well, we can do some cross multiplying here if we want. We're going to end up with -4 multiplied by this binomial. 4x minus 5 squared is equal to -36. Okay, we can divide by the -4. 4x minus 5 squared would have to be 9. Okay, well, there are two possibilities. One possibility is that I'm kind of doing this by completing the square, essentially. 4x minus 5 could equal 3. That's one possibility, right? So we'll call this possibility number 1. All right, if we go and move the 5, by adding 5, we'll have 8. So 4x is equal to 8. Okay, here's one answer. X is equal to 2. That's one possible place. There is another place, though. What if 4x minus 5 was equal to -3? That would be okay. If you squared it, you'd get 9, right? And that's what this says, right? Just something so that if you square it, you get 9. Now when I go and add 5 to both sides, I get 4x is equal to 2. So x could be, it looks like 1/2. It's not showing up super well there, is it? There we go. So two different answers for this one. Okay, we have the main part of the lesson done. Now we're going to look at some odds and ends. This next little section here is, hey, can my calculator do what I did? Because I did a lot of algebra there with the limits. Is there a way my calculator can help me? And the answer is yes, but let's be clear about what you might be asking. In this little box here, we're going to talk about the derivative at a point, like at a specific location. And then in the next box, we'll talk about the derivative in general, kind of our lesson today. So the yellow stuff was from the previous lesson, and then the blue stuff there is today. So looking at the same function we have seen earlier today, if the function is that, then the derivative, the slope finding machine, we saw that that was actually 3x squared, okay, a few pages back. Can my calculator help me out with that? Can it tell me that it's 3x squared? And can it find some numbers for me? So let's first do at a specific location, like at 2, to see, can it tell me what the slope is? And the answer is yes, you can do it. First of all, you could just graph the function. So I'm going to go ahead and put in here y is equal to x cubed. I'm just going to try zoom 4 so I can see it. Yes, okay, so there is x cubed. And now, can I go and find the exact slope at 2? And the answer is, yep, sure. And it's up here under the Calculate menu. So I'm going to just write down the steps here first, and then we'll try it out. So the steps are, after you've graphed it, you want to go second function, because it's up above, and then hit Calculate, which on my calculator is up there in yellow. And then we're going to pick the option that looks like this, dy dx, dy on top of a dx, which we usually just pronounce dy dx. And then you have to type in the point that you want to work at. So if you want to do this at x is equal to 2, you'll have to type that in, and then you hit enter. So on my calculator, here goes. I'm trying to get up to calculate, so second function, calculate. And I'm going to choose this one, which is option number 6. I can scroll down or just hit 6. Now I have to type in where I want it to do the evaluation. I wish it actually was saying like x equals question mark. It's not, but you could just go 2, and it goes, oh yeah, there. So kind of misprogrammed there the way they've done that, but that'll work. We hit enter, and it says here's your answer, 12.000001. Well, your calculator is not as good as you are at doing these. It can't do limits quite as well. So you have to look at that and go, oh, I get it. You're trying to tell me the answer is 12, right? So yeah, 12 is the answer. Great. Now there is a way to do it without actually graphing the function first. You can go on the older calculators like this. I hit the math button, and then I'm going to go down until I find this thing called the numerical derivative, which for me is right there. For me, it's option number 8. And then it opens up this little function, and it wants some very specific things in here. Now, if you have the TI-84, then it does a much nicer job of this. Okay? But for the TI-83, what I'm going to do is just type some information in. I'm going to say, hey, I'm working with the function x cubed. So I put my function in first. Right? So I go, yeah, x cubed, please. Then a comma, which is up above 7. Then I have to tell it what the actual variable is that I'm using. Well, I'm using x's. You might think that that's obvious, but we'll see a few weeks down the road that maybe it isn't. You might have lots of letters on the go. And then a comma, up above the 7, and then the place where you actually want to evaluate it at. And then you say go, and it says, oh, that answer is 12. Okay. So yeah, it's come up with the answer. If you've got the TI-84, as soon as you ask for that numerical derivative, you're going to see something that looks like this. It'll say D with a box, and then a big box here, and then this thing called the evaluation bar, and then x equals, and then another box. And here's how you would fill it out. You would put the x cubed here, you would put the x there, and you would put the 2 here. And then it will go ahead and figure that out for you. Now, that's from the day before, where you're just figuring out at one point. Can you get the calculator to, in general, tell you that the function is 3x squared? Well, it depends. Some very good calculators will do that. They can work with numbers symbolically, just as letters. But the TI-83 and the TI-84 does not. But you can do this. You can actually go and do a whole new function this way. I'm going to put it in under y2. Okay. I'm going to tell it to do the numerical derivative of x cubed. So I go back to the math menu, and I'm going to go down until I find numerical derivative. There it is. And here I could put my function in. I could actually, if I knew how to do it, there's an option to pull up y1, but I'm just going to type it in. It's faster for me probably at this point. There's my function. Again, if you've got the TI-84, it'll look like what you see over here on the left. I put a comma in, and then an x, and on TI-84 you put the x there. And then I put a comma, and now here's normally where I would put in where I want to evaluate it. But I don't want to say 2, otherwise this will always just graph 12. I want to tell it, evaluate this process at every single pixel location that you're at. So I actually put in another x at this point. And then when I ask it to graph it, hey, maybe I'll make this thick so you can see it. So it's going to graph the slope function in a nice thick graph here. So this function right here is actually the slope of the original one. It takes a little while to draw it, right? It's not super fast. Now you might look at that and go, oh, I recognize that. That's 3x squared. But unless you recognize it, you're not going to know for sure that it's actually that function. So yeah, if you go ahead and drop all that in, then you'll see this thing show up. So key things we're going to be putting in here, x cubed an x, and then another x. That's what's unusual. Or if you've got one of those TI-84s, they do a much nicer looking job of this. Okay, in your Y2, when you have all of those little box options, this is what I would put in. I'd put in x cubed x and another x right there, and then it will actually do the graph for you. It'll sketch it out, but it's not going to tell you that it's 3x squared specifically. Okay, you'll have to kind of recognize that. Okay, next example here. Just going to, for the first time, start practicing taking some English and converting it into some math. So I have this example, and it says find the rate of change of a circle's area with respect to its radius at the instant when the radius of the circle is 8 centimeters. And it's like, whoa, what is going on? I don't understand that. All this stuff's coming at me at once. So I might need to just rewrite this into some nice common language. After a week or so, you'll be totally comfortable with all of that. But for now, let's tear this apart. So rate of change. Okay, so they're saying, yeah, can you go and find a slope? That's what they want to know. And they say at the instant. So that's tangent stuff, right? That's like what we've been working on with derivatives. Okay, so they want to know the slope of the tangent of some sort of graph right when the radius happens to be 8. Well, you could imagine doing a little graph in grade 9 for, hey, what does the area of a circle look like as you go and change its radius? Well, we know that area for a circle is pi r squared. And that graph, if we look at just the first quadrant, okay, being a parabola, is going to go like that, right? It's going to curve upwards. And what they're saying is this. Okay, so if I was to convert this to nice everyday language, they're saying, can you please go and find the slope of the area versus radius graph at the moment, right, that instantaneous moment when r equals 8. So they're saying, could you specifically look right here at the moment when the radius of the circle is growing and it's out to 8? What's the slope of the tangent line? Now, kids that are in grade 8, they can tell you what the area of a circle is if the radius is 8, right? They just go, oh yeah, pi times 8 squared. So the area is 201, but that's not what we're after, right? So maybe that's like here, right? 201. What we want to know is if you were to draw in an instantaneous touch it at one point tangent line, what's the slope of that going to be? Hey, no problem. I can ask my calculator to help me out. So I'm just going to go up here, clear all that off. Let's just graph the function. Let's go, okay, pi times, I'll use x for radius squared. And I need to get over to at least 8. Maybe I'll try zoom 6, the standard zoom. I know that goes over to 10. The graph is way off the screen vertically. If I really want to see it, I can go to my window and say, hey, my y-axis, I have to get way up to well, I know it's past 200, right? So how about we go up to 300, tick marks every 100. Yeah, okay, so there's the graph, and I want to know when you're over near 8, what's the exact slope? I'm just going to ask my calculator. So sometimes we're going to do this. Unless it says do it by hand, maybe we'll just pick up our calculator and say, hey, calculator, help me out. Now again, if you have a TI-83, you have to now type in at 8, and it'll say, oh, here's your slope. I have to write 4 decimal places down, 50.2654. Okay, as long as I go to 4 decimal places, that's considered okay. So they didn't want to know the y value of the graph, they wanted to know the slope of the graph. We should actually put in units too, which if you think about it, the units up and down here, these would be like centimeters squared, and these would be centimeters. So it's kind of like centimeters squared per centimeter. I know that reduces, and you could just call it centimeters, but if you want to write it that way, that almost makes more sense. Okay, some other little odds and ends. Number 14, we're going to practice this idea of looking at a limit question and then saying, hey, it looks like somebody is trying to do a derivative. And if I look at this one, I can definitely see the whole derivative thing happening, right? They're doing some sort of f prime of x. And what would the actual function be, right? What function are they working with? Well, up here, I can see them figuring out, y2 and y1. And so that's kind of my tip-off. And I can go, oh, looks like you're squaring things. So this is actually the x squared function. Okay, this one here, what's the machine that they're playing with? And they're putting in x values, right, of x and x plus h. They're putting those into some sort of machine. It looks to me like on this one, geez, it's a mess. I don't know if I'd want to have to do it, but it looks like they're trying to do a derivative of x on top of x squared plus 1. So actually, once you just kind of look at it visually, those ones aren't too bad. Just trying to figure out, hey, what was the function that they were actually using? And here we're using x's and x plus h. Now on the next page, we're going to do the same kind of thing again, but here they're doing it at one specific point, kind of the plan from the day before, right? So you have to figure out, well, what function are they playing with, and what place are they doing it at? So remember, when you kind of see this, this is going to be your your x plus h, and this is just going to be your x, and all of this, that's your y2, and all of that, that's your y1. So when I look at this one, it looks to me like they're playing with the tangent function. That's the machine they're working with, and they are locking in at an x value of 4. This next one, it's a bit confusing until you spot this 1 over h. Let's take that out of there, and let's write it just down here where we normally see it. So the top is going to be some sort of y2 minus y1, and the bottom is just the difference in the x's, just called h. And we're trying to figure out, well, what's the function they're playing with, and then what point are they at? Well, I'm looking for like a number and a number plus h, and I'm looking at it and saying, hey, it's got to be a 2. So I think they're doing this at 2. So what function are they playing with? That one. Stare at it a little bit. I think they're playing with 3 over x. So 3 over 2 and 3 over 2 plus h. Okay, let's play that game again, but now in a different direction. What would it look like to set up the limit to try to find the derivative of cosine? Well, I'd have to go cosine of x plus h minus just the cosine of x, all sitting on top of h. By the way, right now, that is not a limit that you could evaluate, but at least we know how to write the limit down. The same thing is true with this next one. It will not be a limit that you'll know how to do right now, but we can write down what it would have to be. If you want to try to find the derivative, the slope machine for 3 to the x, you'd have to put in x plus h. That's your second x value going in to try to evaluate, figure out what your first or your second y value is, and then subtract, just putting in x, all sitting on top of an h. Okay, this next one, I found this one. It's kind of a neat question. It was shown to me and I thought, oh yeah, this is kind of a neat one to work with. And the reason why this question exists is just because you can't put it into your calculator. You have to know how the derivative game works, and then it's actually quite nice. And somebody's saying, hey, can you go and find the derivative of this function? And here are a couple of properties that you might need to know. And you look at it and go like, what is going on? Well, just get started. Don't hesitate to try here, right? So we're going to go and do a limit. It's going to be a grade 10 slope, right? And I'm just going to go and do the limit. I need a little more room there. Try that again. It's going to be a limit as h goes to 0. I'll have my h in the bottom. I'm going to do f of x plus h in the top minus f of x. Okay, well, what is this function? And they're not telling you. But they do tell you that if you ever have to do f of x plus something, then this might be helpful. Yeah, okay. Well, I don't have a y, but I have an h. I guess that's what's happening right here. So wherever I see a y, right, it's like I have that h there. Okay, so I can rewrite this top based on this property. And you have to remember that this question exists simply as a way to demonstrate that you know how to set up the limit and you can't use your calculator to help. So this would be, figuring out this top part here, this would be f of x plus f of h. I'm just following their pattern based on this property for this function, plus x cubed h plus xh cubed. They're all of that whole thing. That's just me doing this. Now subtract off f of x. Okay, minus f of x. And all of that sits on top of h. Oh, hey, look, there's that issue where the non-h terms kind of go away. That's gone with that. And what are we left with? All right, well, let's see if we can tidy this up here a little bit. We're going to have this interesting limit. Let's see what we have. Limit as h goes to 0. Now I've noticed they've got two terms that have h's in them. I'm kind of accustomed to seeing that, but this one, what's the deal here? I mean, it's not like you can hack this h off. That's inside the f function. But maybe I'll split this up into two different limits. I could do the limit of f of h on top of h. There, that'll deal with that part right there. Now let's deal with the rest of it. What about those two things sitting on top of an h? We'll just do that as a separate limit. Plus the limit as h goes to 0. What I like about those last two things is they have a common h. So I can go and extract them and pull them out front. And I'll have x cubed plus x h squared, all sitting on top of an h. Okay, well actually, this function here, like I'm looking at that going, how am I going to do that? Well, look, they told you. They said if you're ever doing this limit, f of something on top of that same something, and the something's going to 0, yeah, sure, I'm doing it. It's just I've got it as h, well, they've got it as x. That's just 2. So I can just go, hey, I don't know why, but you told me that that's just 2. And now this next part, well, again, I'm only going to put numbers in that are close to 0 for h. I'm not actually putting 0 in. So those reduce. And now I am going to go and do direct substitution. And I'm not left with much except an x cubed. So there's my answer. The derivative for this function that you're not even telling me really about, you're just giving me a couple of properties. The derivative would have to be 2 plus x cubed. Okay, one more page of slightly new stuff and then just one piece of paper that's got some review on it. Let's just talk about different ways that math people like to talk about these slopes that we're working on. In grade 10, we had 2 points that were widely spaced, and we said, oh yeah, if you want to find the slope in grade 10, well, we can write it like this. Big changes in y divided by big changes in x. Some increments in y divided by an increment in x. Well, now we're working with really, really small changes, right? These limits. And there's some options for how you can write that down. Today, we've been looking at the derivative as a whole brand new function. And there are a couple of ways that you can write that down. And you've seen me use that apostrophe. Well, that's actually Isaac Newton's way of writing that down. And he would say, oh, you could write it as f prime of x. Or if you want, he sometimes goes y prime of x, right? Because the y's are functions of x's. And that was Isaac Newton's way of writing this down, but he is one of two people that kind of invented calculus at the exact same time. So that's the Newtonian way of writing it down, and a lot of students like it because it's short and simple. But there was another inventor of calculus, and he has a completely different notation. And at first glance, you're going to say, oh, I don't like it. I don't like it, it's too long, it's too hard to write down, it's not as nice and quick as the Newtonian way of writing it down, but it is actually better. It's actually got more information packed into it. So here are 4 different ways you might write that down. Kind of going back to this grade 10 idea of delta y on top of delta x, these delta symbols, those are capital Greek letter deltas, meaning big change. A lowercase Greek letter delta looks a lot like our letter D. And so we pick up on that and say, hey, why don't we write this as some small change in f of x divided by some small change in x, which is kind of what our calculator does, right? Our calculator says, yeah, you could write that as dy dx. And so those mean small changes in y on top of small changes in x. You can actually take the function and the y and kind of pull them down out front of the fraction, and it's very, very common to also write it like this. You can say d dx, which is actually an instruction to you. It says, hey, go and find the derivative. And you're like, well, the derivative of what? And you can put the f of x down out front, and it says, I'd like you to go find the derivative of that, please. You can do it with y as well, right? You could say, hey, can you go and find d dx? Can you go and find the derivative of y? And so all of those mean the same thing. What's nice about the Leibniz notation is that it has packaged into it that you're doing a derivative with respect to x, that x is actually your variable. Now, the day before this one, we talked about derivatives at a point, like, for example, at x equals 2. So how do you write that down? Well, two different options depending on whether you're Newton or Leibniz. So if you're Newton, he would say, oh, well, I would just write that like this, f prime at 2, or maybe y prime at 2. And that's great. That tells you to go and find the exact slope figured out at 2. Leibniz notation is not as nice. Okay? He would say, well, how about we go and figure out the derivative, and then when you're done, could you please go and evaluate it? So this bar like this in math means let's go evaluate that at the time when x is equal to 2. Or he might write it, hey, let's go and find dy dx. And once you've got that algebra, can you go and evaluate it at the moment when x is equal to 2? And yeah, you can pull the function down out front. You could say, oh yeah, can we go and do a derivative, please, of f of x? And then when you've got that, could you please go and evaluate it at x is equal to 2? And all of those are fine, but here's something that you cannot write down because it has a big order of operations kind of blunder to it. This is unacceptable. You can't write d f of 2 dx. Because no matter what, the answer to that is 0. F of 2 is some sort of number, and then this is saying, oh, can you go and do, it's basically saying this, can you go and do the derivative of just a number? And the derivative of a number is like asking, hey, what's the slope of a constant function? And it's always just equal to 0. So we don't want to do that, right? You do actually have to say, no, df dx, and then evaluate it at x is equal to 2. Okay, just a little bit of vocabulary. Let's talk about this big crazy word here, differentiability. A function is differentiable at some point if it has a valid derivative there. So if somebody says, hey, is this function differentiable at x is equal to 2, what they're saying is, does this function have a very clear, a well-defined tangent line? If you had a ruler and you were to walk up to the function and somebody said, draw the tangent line at this location, would you know what to do? And the answer is, yeah, usually I would most of the time, unless the graph has some weird problem, like some sort of cusp in it like that, then I wouldn't know what to do. Or if the graph has a big hole in it, right, like this, then I wouldn't know what to do exactly, not for sure, so it's not differentiable there. Or maybe the graph has an asymptote, right at that spot, then there's no tangent line there. So to be differentiable means that it has a clear tangent line. Some other things we can say, if a function is differentiable, okay, if it is that, let's go with some common language. They're basically saying if it's smooth, right? It has to be smooth to have a tangent line to it. If it's smooth, if it's differentiable, if it has a tangent line, then the function surely is continuous there. It has to be connected. We talked about this a few days ago. So a graph that looks like this, it might look smooth, but if it has a hole in it, we would say, oh, no, it's not smooth at that point. I don't know exactly what I have to do for drawing in tangent lines because it's not smooth there. Like, should it go like this or like that? I don't know. So we're going to say, no tangent line if it's got a hole in it. it has to be continuous in order for us to have a chance. A function that is connected, that is continuous, if it's connected, it may or may not be differentiable. This is that whole cat-animal thing. So it's a challenge to be differentiable. You have to first be continuous. So it's like saying if a function is a cat, then it surely is an animal. But the next line says a function that is an animal may or may not be a cat. Here are some ideas, right? What if I've got a graph that, like I said, goes up to a corner like that, to a cusp? I don't know what I'm supposed to do if I'm asked to draw in a tangent line. The graph's definitely connected there. You know I can follow it along with my pen in blue, but I don't know how to draw in a tangent line. And so that one point right there where it has this big issue, a point like this where we're continuous but not differentiable, that's a point of non-differentiability. And this last issue, if something is not an animal, it can never be a cat. You can read that this way. A function that is not continuous it is never differentiable. That's a rule. You have to be connected in order to be smooth. You cannot be smooth if you're not connected. That's the end of the theory. Let's take a look now just at a couple of pieces of paper that have some review material on them, just to kind of show you what we've seen in this chapter. So we started off the chapter by taking limits. We looked at how we could do it graphically, numerically, or algebraically. As far as the graphical and numerical thing went, that was when, if I can just put this in, if this makes any sense, remember the idea of the little green curtain, right? You know, don't look behind the green curtain. The little Wizard of Oz thing. Just look close to those values. Here, close to values where x is equal to 2. And then you could go, oh, I kind of highlighted the wrong thing there. Then you could go and look at the y values close to that. After we looked at just normal limits, we talked about, well, what about one-sided limits? What about a graph like this, a function by piece, where on one part of the day, before you get to 1, we're going to be drawing a parabola. We're going to be going kind of like, oh, what's it going to do? We're going to hit here, here, and there. We're going to go like that. That's the first branch. But then later on, it does this other branch, and that ends up being up here, kind of going like this. So there's a function. It does pass the vertical line test. But what about limits? Well, it doesn't have a limit at x is equal to 1. Not a full limit, but it does have one-sided limits. You can say, oh, well, on that left side, kind of in blue, it looks like the limit as you approach 1 from the low side is negative 1. That was the y value that we were heading towards when we got near x is equal to 1. But on the upper branch, the right-hand branch, working back to x equals 1, it looks like the y value is limiting to 4. All right, next thing we saw, continuity. In order for something to be continuous, all three of these things have to be the same. You have to have the limit of the function on the left and the right side. They have to be equal. And then it also has to equal the number. Okay, you have to have all three things. Let me just highlight where those three things are here. The limit from the left and the limit from the right has to eventually equal the function at that point. All three things have to be in agreement. That's the definition for it being continuous. So if somebody asks you, hey, is that function continuous? And you say yes, and they say justify it, you can't say, well, I can draw it without lifting my pen, or I can just see it, or it's all beautifully connected. Those are great ways to describe it in common language, but to write it down mathematically, you'd have to say this left limit equals this right limit, and it equals the function at that point. That's why I know this thing is definitely continuous. Then we started getting ready to do derivatives. We looked at average rates of change. So whenever you see the word rate of change, or the phrase rate of change, you should be thinking slope. And so this average rate of change is an average slope. That's like saying, let's find the average rate of change from x is equal to 1 all the way out to another x value of x is equal to 3. So from there to there. And the whole idea of this average rate of change is that you're drawing in, at least in your mind, this thing called the secant line, right? That's that line right there. And you could say, oh yeah, okay, I'm just going to do a big change in y on top of a big change in x. Here it would be 10 minus 2 all on top of 3 minus 1. That's nice, but what's better is if we can do an instantaneous rate of change. So again, rate of change, this just means slope. But to do it instantaneously means we're going to do it at one point only. So notice this one says, oh yeah, instantaneously at x is equal to 1. So with limits, we were finding the exact slope of a tangent line that just comes by and touches it in one place only. Okay, that's the whole idea of working with derivatives. Now, when you go to do that, we had two options for finding that derivative. You could do it at a point, like x equals 1, or you could do it everywhere, which was even better. And that's what's on our last page here. Okay, so calculating derivatives at a point, that's when they lock in a number for you. They would say, oh yeah, we're going to lock in at x is equal to 2, right? A is equal to 2. That's the only place we're going to be at. Can you please go ahead and find the slope of the tangent line there? And you say, sure. Let me go with a couple of different x values. My first x value is the one you gave me. Thank you very much. It's 2, right? Or whatever number it is that they give you, right? That's the A. And then my second x value will be at that place and a little bit more. And so way out here somewhere is going to be some other point. Okay, right there where you say, oh yeah, that's at 2 plus h. And then you go through that limit, right? So you'd have a 2 here and a 2 there. And then you're finding the slope of that line and you're limiting, bringing them together. Really, all you're doing is, I want you to think of this, you're just doing a grade 10 approach. Your plan is to do this. But you're doing it where those 2 points, the x values get really, really close together. And h just talks about how far they are apart. So we just want to bring that h value towards 0. The big problem is figuring out the y2 is usually a big mess, right? You often have to do a whole bunch of multiplying there. The last thing we saw that today, even better than picking a number, you don't pick a number. You don't pick 2 right off the start. You say, well, how about I just say that I'm going to pick a point here, and I don't want to lock in, so I'll just call this point x. And I want to try to find the exact slope of the tangent line at any spot people might want to talk about. Well, I'll get there doing that limit, but I do need another point. So my other point will be a little farther down the road. This will be at x plus h. And so h, all week long here, has just been how far apart are these 2 points in their x values. But we're not going to lock in at 2. We're going to say, no. Let's just keep this wide open as being some sort of value called x, right? So that goes in here and in there. And that's it. That's how we can find these exact slopes of tangent lines, which is one of the 2 big quests in calculus. And we'll be now working with this all through Chapter 3 and through Chapter 4, looking at different applications of working with these derivatives.